Welcome to another cosmology talk. This week I have with me Deanna Hooper, who is currently a postdoc at Brussels Uni and was actually last week's speaker's PhD student up until the end of last year at Aachen University. She's had a couple of recent interesting papers, but today in particular she'll be talking about one titled The Synergy Between CMB Spectral Distortions and Anisotropies. It's quite a long paper, which is makes it ever more useful that we get a nice talk, breaking it all down into just 50 minutes. So thanks, Deanna, for doing this. And yeah, do you want to start with just sort of telling us what you did that, in the paper?
Yeah, so good morning or good evening for you at least. So in this paper, we look at what is basically an untapped resource of the CMB. So we're all very much accustomed to CMB anisotropies. We have measurements from Planck, but there's more information hidden within the CMB in the form of the deviation from a perfect black body. And this is something that has very much not been exploited to its full potential. And in this paper, we wanted to show that this has a perfect synergy and combination with the standard CMB measurements, to the point that if you make the predictions for any model, for an example, annihilating dark matter, decaying dark matter, primordial black hole evaporation, you can actually explore a whole new region of parameter space with spectral distortions that you don't cover with anisotropies. So in order to exploit this synergy and this combination, the first step was actually to implement the full calculation of spectral distortions in our standard Boltzmann solver class. So basically now at the click of a button, you can produce both the anisotropy prediction and the spectral distortion prediction for the same model.
Cool. So if you just wanted the people listening to this talk to just take two simple things away and nothing else, what would those two things be?
So the first thing would be that spectral distortions are really an untapped resource, and I think they are the future of the CMB. And even with future CMB missions, spectral distortions will allow us to improve by several orders of magnitude in some regions of parameter space. And my other takeaway message would be we now have a really powerful tool in the form of class 3, which is the updated version of the public code class, which will be able to compute spectral distortions and anisotropies in parallel without too much loss of time.
Oh, cool. Yeah, so the next question would then be why, you answered this a little bit already, but maybe go into a bit more detail. Why was this the particular problem you wanted to solve? Why wasn't it solved until now? What's the background? We know the CMB anisotropies are extremely well measured by Planck, down to the order of percent level precision. But the measurements of the spectrum of these photons, we actually only have one observation, which is from the COBE-FIRAS mission, which is 25 years ago. I find it amazing that that's so long ago. But yeah,
long ago, like COBE-FIRAS is already 25 years.
Yeah.
Impressive. So this was obviously a pioneering mission, and it did give us the overall temperature of this black body. And it showed us that there cannot be deviations from the black body above 10 to the minus 5. So it did put a very stringent bound. Now, the problem is that even within Lambda CDM, we predict spectral distortions of the order of 10 to the minus 8. So this is 3 orders of magnitude below what COBE-FIRAS measured. And the thing is, this is a very clear prediction from Lambda CDM. So if we have a spectral distortions mission and we do not measure anisotropy distortions at the level of 10 to the minus 8, it means Lambda CDM is wrong. It is a clear testable prediction from Lambda CDM, and we haven't yet tested this. But it's not just within Lambda CDM. There's a lot of exotic models. Basically, any model that injects energy into the CMB photons before recombination is going to produce spectral distortions. And these spectral distortions vary of the order of 10 to the minus 8, 10 to the minus 9. And it really allows us to distinguish between different models. For an example, there are some solutions to the small scale crisis in cosmology that can actually be disentangled with spectral distortions. An example, models of late kinetic decoupling could actually be disentangled. I should have turned off my screensaver there. So these models could actually be disentangled with a spectral distortions mission. And it's a place where we feel like the observation is really lagging behind the theory, because the theory of spectral distortions is extremely well understood, and it's been studied for 30, 40 years now, especially with the advance of some codes by Jens Ströber mainly We had Cosmotherm, Cosmospec. These are codes that were designed to study spectral distortions. We have a very, very good understanding, to the point that we can say from Lambda CDM, we predict 10 to the minus 8. From primordial black holes, we predict 10 to the minus 9. And the observations are just lagging behind. And it's not through lack of trying. People have been pushing for a spectral distortions mission, but it's never received funding.
So it hasn't been that like the technology's been lacking. Like this is something that could have happened 15 years ago, or
yeah. So 10 years ago there was already a proposal for the PIXI mission, which would have a sensitivity of 10 to the minus 8, and that was with technology from 10 years ago. With technology we have today, we can push this to 10 to the minus 9. So there's already a new proposal for PRISM mission, which pushes it to 10 to the minus 9.
This is a little bit off topic, but it's something I've always wondered. So I'm gonna ask you. It's kind of about the politics of science. Do you know why it has taken this long? Because 25 years is just crazy, and it's not like we're measuring it now, right? Like it's going to be more than 25 years by the time it gets measured.
Yeah, so one of the problems, of course, I paint this lovely picture that we do have the technology, but there is going to be the big problem of foreground removal, which was already an issue with CMB anisotropies. But it's something that, again, has been worked out within the community. And there's a group of people who really have mapped exactly what foreground removal we're going to need and what's going to be needed for this. So it's something that I think a lot of people have overlooked because it's only been a small part of the community pushing for this. But I do think it's gaining more and more attention now, especially now that there's potential tensions. And we actually asked the question of, is Lambda CDM really the good model? Being able to test the prediction of Lambda CDM feels like something that we should be doing. So I know there was a proposal for the mission, the PIXI mission, which could have done this, and it didn't receive funding. There's now hopes that PRISM will receive funding. And in fact, in the NASA roadmap, there is now spectral distortions included. So it's not yet anything officially approved, but they are looking at it as well.
Okay, so the expectation would be that, I don't know, 10 years from now, these measurements will have been made, or is 10 years too optimistic?
I think 10 years is too optimistic because, of course, first the project needs to be funded, then it needs to be built, and then it needs to take measurements. But I really think within 15 to 20 years, this is a completely feasible measurement. And by then, technology would have progressed enough that we will be pushing this threshold even more. Okay, cool.
So do you have anything more to say on the sort of background motivation, or do you want to start going into like the nitty-gritty of the paper?
Just another one of our motivations. So the paper is very long, as you already mentioned before, but part of the reason is because it's also a review paper. So we wanted to review the whole formalism of the topic. And our motivation for this was that in several different papers and in the existing code, there was different notation. Sometimes it can be a bit overwhelming to get into the topic. So our idea was really to streamline everything in a nice review paper, which also goes hand in hand with the implementation in our CMB code, because then all of the notation is already explained in the paper. So then once you pick up class 3, where you will be able to do everything in parallel, you should be able to follow the full implementation if you want to. Of course, you don't have to understand all of the technical details to use the code.
And people who are familiar
was really to have this streamlined package.
And people familiar with class it'll be quite straightforward to then get the spectral distortions out as well.
If you've used class before, then you always ask class for different outputs, like the CMB anisotropies, the matter power spectrum, and now you just add another thing of I want spectral distortions. And if you don't tell it anything else, it will take some default values and produce the spectral distortions of your model, assuming it's a model that we've coded the spectral distortions for. Yep.
Cool. So anything else, or do you want to? Let's get into the nitty-gritty.
Yeah, let's get into the details.
Cool. So you can share your screen if you want. Yep.
Okay, so I just want to mention here that this paper was actually led by 2 students in Aachen. One is no longer in Aachen. That's Matteo Luca and Neil Schoenberg, and they really did a huge amount of amazing work for this paper. So I just want to mention that here, that they really did so much for this paper. Okay. So the idea here is we have these CMB and spectral distortions, which are deviations from the black body of the CMB. There's a lot of technicalities involved here, so I'm just going to present the main idea. Okay. Now, depending when the spectral distortions come about in the history of the universe, we're going to have different types of distortions. So in the very, very early universe, thermalization is very efficient. The thermalization of the CMB photons is very efficient. So the only type of distortion you're going to be able to produce is in the form of a temperature shift, which is what we call here the T distortions or the G distortions. And it's the third contribution you see here, the delta IT. This is the temperature shift distortion. And this is the one that is going to be dominant in the very early universe.
Okay, and that would just be seen as a temperature anisotropy. You wouldn't see that in any other way, or?
Yeah, this would just be purely absorbed as a deviation of the temperature of the CMB.
Okay.
So this would just shift the overall temperature. Of course, this would already be what we measure. So this is essentially something that would be unmeasurable to us. Then as the universe gets cooler, so at the next redshift, around redshift of 10 to the 5 or so, you're more likely to produce the Y-type distortion, which are essentially like a Compton-like distortion. So it's related to Compton scattering. These will become efficient after the temperature shift distortion. And then later on, you shift to the mu distortions, which are the chemical potential distortions. But this is not a clean transition. So you do actually get a period where you have both Y distortions and mu distortions. And this is what we call the Y mu period. So you can separate different phases of the universe, where first you'll have the temperature shift, then you'll have Y, then you'll have a mix, then you'll have chemical potential like distortions. And then there's the final contribution, which is the residual distortion, which is basically everything else. And unfortunately, this everything else is a contribution that is going to be there, and it can't really be measured, but it can be taken into account within the full calculation. So the residual is going to be orders of magnitude smaller than the other contributions, but it is going to be there.
And this whole thing is like a frequency dependent thing. So the Y distortions affect the frequencies in a particular, the intensity is a function of frequency in a particular way, and maybe that's what you're getting to.
That's exactly what I was about to say here, that within these distortions, we can decompose it into two main parts. For each one, we have like the lowercase and the uppercase. So for the Y distortion, we would have the Y and then this function Y of X, or Y of the frequency. So the shape of the distortion is going to depend on the photon frequency. So this also means that when you're using a different detector, this is something that needs to be taken into consideration, because different detectors are going to have different frequencies that they study and different binnings of the frequency. So this is something that class needs to know about as well. So by default, class would assume Pixie-like mission, but it's very, very easy to change because you just need to pass 4 new parameters to class. But this is something that will also depend. So obviously the prediction itself will not depend on the satellite, but the way you do the binning and the part of this that you're going to observe will depend on your setup.
Is that because like the detector, even if one says, I don't know, 300 gigahertz, it's not actually measuring a delta function at 300 gigahertz. It's some combination of 290 all the way to 310 or something like that.
Exactly. You're going to have usually you have different channels, different frequency bins, and this is going to impact the way that you're going to be able to do the measurements.
How many frequency bins would Pixie or Prism have? Order of magnitude.
So Prism would have bins of 15 hertz in a range of about 3,000.
Okay, so the answer is lots.
A lot, yes. I think it works out to about 600 to 900 frequency bins.
Because Planck, I guess, had what, like 9 or so. So it really is just
that was different channels. So it's slightly different, but that was the channels that they were measuring. Here, it's really how we bin the frequencies. It's a similar idea, though.
Okay, yeah.
And the other part that you have is the amplitude. And the amplitude of the spectral distortions here is actually going to depend on the injected energy. So this is really the process that is leading to the spectral distortions. Now, the good thing is that this shape can be mapped once, and then it doesn't need to be recomputed for every model, because the shape itself does not depend on what you're injecting. It just depends on the overall specifications. But then this amplitude itself can be further broken down into 2 components. So we always express this as deviations with respect to the background photon density. And there's going to be 2 components here. There's going to be a model-dependent heating function, which is going to encode all of the physics of your model, and model-independent branching ratios, which have already been catalogued, and this is where the redshift dependence comes in. So the branching ratios is what tells you if you have more Y-like distortions, more chemical potential-like distortions, more temperature shift distortions. And this has already been pre-computed, and you don't need to recompute this for your model.
And does branching ratio mean that you've got some new species that's decaying into stuff, and it's like how much electrons, how much photons? Or?
Yeah, that's normally what we think of with branching ratios, and the name is slightly misleading, but it's more what contribution goes into each of the different types of distortions.
I see, okay.
Rather than how much into each particle, it's how much goes into each distortion.
How much into Y, how much into mu? how much into
exactly.
T.
So how much of this total distortion will be in the form of mu, how much in the form of y, and then the branching ratios really tells you at which redshift each one becomes more dominant. So depending which redshift you're at, you'll have more y, you'll have more mu type distortions.
Cool.
But the heating function here, this model dependent heating function, this is really the key issue here, because if you know the heating function of your model, you can calculate spectral distortions. Of course, that is the simplified takeaway statement of a year's work into a code. And the biggest question is how you go from injected energy to heating function, because it's not necessarily a one-to-one correlation.
Okay.
But there are ways that you can translate the heating function, the energy injected, based on whether it's injected, deposited energy, how it influences the CMB photons. You can extract this heating function.
Okay.
We've set up class in a way now, so class is always very modular, so it only computes exactly what you need. So if you're only running up to thermodynamics, you only care about the thermodynamical evolution, you're not going to compute the primordial power spectrum, for example. And now within class, there are two new modules where one will compute the heating functions and one will compute spectral distortions. Because they're called independently of everything else, you can still use class the way you've always used it without noticing this if you don't want it, which is nice. I should mention here that the heating functions and our new heating module and our new distortion module are actually based on previous codes, but independent codes that were not unified. So for the heating functions in class, there was actually a version called ExoClass by Polan and Stocker, where they looked at the energy injection coming from several different models. And this has been rewritten and incorporated into our code. And the spectral distortions calculation is based on Cosmotherm by Jens Schrober, which has also now been rewritten and integrated into our code, streamlined.
Okay.
So this is the only slide of formulas I'm going to show. This is the basic takeaway. And if you want more details on this, we wrote the review on the topic. So that's the first 20 pages of the paper condensed into one slide.
Cool.
So I'm going to focus on the branching ratios here just a minute, because this is, as I said, this does not depend on the model that you're looking at. So these are the branching ratios that we have computed with our modified version of class. So the different colors show the different contributions. So in red is the contribution coming from the Y era, or the Y distortions. The green ones are the mu distortions. The blue ones are the temperature shift G-like distortions. And the residual is the pink one, magenta one. These should always add up to 1, because it's normalized in the way where the branching ratio should always add up to 1.
Okay.
And I've also highlighted the different eras here. So you can see the higher redshift is on the right of the plot, and we have the G era first, then the mu era, then the Y mu era, then the Y era. I actually think those are flipped now. But yeah, you have these different regions. And at each region, one of the contributions becomes more dominant. But they always add up to 1. So then depending on which redshift you're focusing on, you're going to have a different contribution from Y or from mu distortions. And the residual is always going to be there in the background.
Okay, and you say they add up to 1, and then some of them are greater than 1 at the same time as others are less than 1. I guess the normal branching ratio thing, that would just be like a physical impossibility. But here, it's, as you said, it's not the same sort of meaning of branching ratio.
Yeah, it's not the same, because you can have some things injecting energy and some kind of subtracting energy from your background medium. So this is how you get some things that are slightly less than 1 and some that are higher than 1. I'm not sure if you can see in the legend here, but the magenta line has been multiplied by 10, because else it would be substantially lower and not really visible on the plots. So the residual is just this background one that you always have there.
So the main thing countering the mu distortion is actually the T distortion.
Exactly, the temperature shift distortion.
Okay. And why does this have to add up to 1? Like, what exactly does it mean for a Y distortion to be 1?
So the reason it adds up to 1 is because we're looking at these deviations from the photon energy, and we assume that no distortions, or the perfect black body, is the best case. So in the best case scenario, you have black body. So then any deviations are going to be changing this kind of budget equation. Okay. So it's always going to add up to 1. If you have mu distortions of 1, it just means that you have the only contribution being mu distortions and no other distortions.
Oh, I see. Okay.
So you can see very close to recombination on the left of the plots. The only one you have is this Y distortion. Everything else is no longer significant. So at that point, it's like the Y distortion accounts for 100% of spectral distortions.
Okay. And if the Y distortion became 100% bigger, it would still be 1 because it's bigger, but it's still only from the Y distortion. I get it.
Exactly.
Okay.
It's like the sum of the individual contributions. So this should always add up to the total, which is normalized to 1.
Okay. And why is it, sorry for dwelling on this, but why can it have a sign? Like, why can there be a positive mu distortion, but a negative T distortion?
Yeah, this is just really related to the way it's affecting the photon energy, whether it's subtracting or adding to the photon energy. So at different regions, you're going to have different dominant contributions, but the idea is we have normalized it to this default radiation level. So then any deviations are either going to be adding or subtracting to this.
Okay, so a positive is more energy and like averaged over all frequencies in some way?
Yeah. So to really get how this is related to the frequency, you would then need to see the shape of each individual distortion. So I don't actually have the shape here. If I go back to the previous slide, the branching ratio is just these J functions, but then you have these shape functions, and the shape functions really tell you so how it depends on the frequency. And this is also something that is very easy to calculate with our new code. And these branching ratios do not need to be recomputed for every model. So these branching ratios are stored, and unless you're messing up the branching ratios, which you shouldn't really do because it's model independent, these don't need to be recomputed.
Okay,
so then we can look at the different types of signal that we get. So just flashing the previous slide before, what I was showing now was the branching ratios. But now instead I'm going to focus on this total distortion to the photon intensity spectrum. So the thing that we would actually measure within the CMB distortions. So I can show here for several different models what this would look like. So we are showing here the absolute value of this intensity spectrum, which is why you're going to have a negative branch and a positive branch. So I've mentioned here which is a negative branch and which is a positive branch of each model. So all of the ones shown here are the basic spectral distortions we would expect within Lambda CDM. So these are not all the contributions, there's 1 or 2 missing. But within Lambda CDM, one of the biggest causes of spectral distortions is going to be the dissipation of acoustic waves in the early universe. And this is going to lead to the red solid line here, which the dotted black line in the background is PBH sensitivity. So this is the mission that was proposed 10 years ago, which would have a sensitivity of the order of 10 to the minus 9 in terms of Y and mu distortions. And here you can see that most of this is just below the sensitivity of PBH. So it would not be detectable by PBH except in some frequency bins. And the cool thing is then you also have the baryon calling, which is a much smaller contribution, but it is a contribution that we expect within Lambda CDM. And the idea is if we don't measure this red solid line, something is wrong with Lambda CDM because this red solid line is a prediction of Lambda CDM. Now the FIRAS sensitivity is not listed here, it would be off the plot, it would be at the top of the plot. So this is something that is a testable prediction of Lambda CDM, we're just missing the satellite to do it for us. So the two lines we're showing here in dashed red and dotted red are tiny deviations to Lambda CDM. So the dashed one is what would happen if we change the running of the spectral index. So we know that Planck has measured the running to be very close to 0. And we just tested what would happen if it's minus 0.01. And you can see that it does change. The signal is different to the case where it's fixed to its default value of 0. In the dot dash line, we also tried the extreme case of what is n effective is equal to 10. Now, of course, we know that n effective is not equal to 10, but this was just to show how much it can actually influence spectral distortions. So we see that the signal is different, and it is different in a region that PBH would be sensitive to. So PBH would be able to measure these differences. And these are the ones that are predicted within Lambda CDM and 2 basic extensions, so with the running and n effective. Okay, so here we're looking at other really cool models. For an example, annihilating dark matter and decaying dark matter. So we've left in the dissipation of acoustic waves as the black one in the background, just as a reference. So that's what we expect from Lambda CDM, or that's the biggest contribution coming from Lambda CDM. Again, the dotted black line is PBH sensitivity for reference. In the red, we're showing a sample case of annihilating dark matter. So we didn't focus too much on what the dark matter is annihilating into. It's just a generic case with a specific annihilation function. And we see that this is actually a smaller contribution than Lambda CDM. So this means that PIXI itself would not detect this annihilating dark matter. But if we look at the decaying dark matter case in green, we can see that it's about 1 order of magnitude higher than the Lambda CDM prediction. So this is something that PIXI would absolutely be able to measure. So with this in mind, it's the first hint that we have that decaying dark matter is something that we will be able to constrain with spectral distortions. So later on, I'll get on to exactly how much we can constrain with these.
And would COBE still not even be visible on this plot, or is it just starting to sneak in?
COBE-FIRAS would be the top edge of the plot, essentially. It's orders of magnitude off. So I just want to flash one example of heating function here, because I've been focusing on the intensity spectrum, but I mentioned that a big part of the work was quantifying this heating function. So this is just to give you an idea of what the heating functions look like. So it's for the same cases as in the previous plot. So we have the dissipation of acoustic waves, annihilating dark matter, which we see the heating function is substantially less than Lambda CDM, and the decaying dark matter case, which we see is substantially higher, especially at specific redshifts. This is enhanced dramatically. So this is really the signal that we would hope to see. This heating function would produce the previous plot, which is what we measure in the sky. And the other very interesting case we looked at is primordial black hole evaporation. Now, primordial black holes obviously have gained a lot of attention lately, and they are a really cool topic to work on. And we focus on 2 main parameters of the primordial black hole. So the fraction of primordial black holes that account for dark matter, and the primordial black hole mass, where we assume monochromatic distribution. And this is just for 2 test cases that we chose. And you can see that as you increase the mass of this primordial black hole species, you really push the signal above Lambda CDM predictions. So this is, again, something that we really expect spectral distortions to be able to constrain. So this is really just setting the scene of this is what we hope to do. This is what our new code can do. Now, the next step, of course, is actually making mock data and seeing what we would be able to do with future missions. So for this, we use the parameter inference code MontePython. Now, MontePython usually relies on existing data. So it has likelihoods for Planck, for basically any known experiment, you have a likelihood in MontePython. But it also has the ability of producing mock data, so mock likelihoods for future missions. So here you give it an input cosmology, which we call our fiducial, and we always take our fiducial to be Lambda CDM. And then you generate mock data around Lambda CDM with some specific uncertainty. And then you see, with a mission of these characteristics, what deviations from Lambda CDM would I be able to measure? And MontePython already had these mock likelihoods for CMB missions. So this is Lightbird, CMB stage 4, PICO. It also has mock likelihoods for large-scale structure missions like Euclid and SKA. So then we added mock likelihoods for PIXI, for PRISM. We added the existing likelihood of FIRAS. Then we ran some tests to compare exactly how these future missions are going to constrain the different parameters. So the first case we focus on is one of the basic cases that you might be interested in, which is Lambda CDM plus running. So we vary the 6 Lambda CDM parameters plus the running of the spectral index. And we looked at 5 different cases. So in gray, which you can barely see, is Planck. In blue is Planck plus FIRAS. So these are concluded missions. And for these, we have the data. And we already see that the blue and the gray everywhere completely overlap because FIRAS did not add substantially on top of Planck. Then in green, we have Planck plus PIXI. So this is what we would measure if we use the PIXI-like mission together with the data from Planck. In red, we show the next best CMB anisotropy combination. So this is CMB stage 4 and Lightbird. Both of these missions have been approved and are set to be built within the next decade. These will focus on temperature and polarization anisotropy. So it's like the next step after Planck, but still measuring the same quantities that Planck measured. And then in yellow, we say, what if we actually had a PRISM-like mission, which is what the technology allows now? And we combine it with the futuristic CMB missions, because by the time we get data from PRISM, we would have data from Lightbird and CMB, so why wouldn't we use them? So then on the left plot here, I show the two-dimensional posterior contours coming for the three main parameters involved. So NS, AS, and the running. And if we focus on, so the diagonal elements are just the one-dimensional posteriors, we can ignore those. So of the three actual contour plots, if we focus on the one on the top left, this is how AS and NS change. And here we see that the yellow and the red completely overlap. So basically Lightbird and CMBS4 will do exactly the same as Lightbird and CMBS4 plus Prism. So in that plot, Prism is not helping. But now if we actually move to the two bottom ones where we have the running, we can first compare the blue to the green. This is Planck plus FIRAS and Planck plus Pixie. And we see that the error bars on the running already shrink a lot. So this means we would get an increased sensitivity to the running. We can then compare the red and the yellow, which are what we would hope to have in the future. And again, we see that going from Lightbird plus CMBS4 to Lightbird CMBS4 plus Prism, we gain a lot, about an order of magnitude on the error bars of the running. So this means that we've taken our fiducial value to be the running equal -1, which is what CMB has measured, or what Planck has measured. So this is our fiducial value, and any deviations from this would have to be within the yellow bars, or Prism would measure them. So we see here that Prism would really contribute substantially on top of the existing missions that we're going to have. So this is our first test case. On the right, I'm just showing the sensitivity of these individual missions to the Y and mu parameters. So the blue is what FIRAS gave us. So these are the specific spectral distortions parameters. So the blue one, again, is what Planck plus FIRAS gave us. The green one is what Pixie would give us. And the yellow one is what Prism would give us. And we can really see how much this is going to improve. And Prism is already within reach of current technology.
And is the reason that the spectral index and amplitude is largely unaffected, but the running is affected, is that it's the physics that causes the spectral distortions is on smaller scales, isn't it? It's this dissipation of the acoustic waves is happening on smaller scales.
Yeah, so if I go back to the thing that we have here, these heating functions, let's take the black one as the example. Now, AS and NS will not affect the heating function substantially. They will leave the heating function mostly unaffected because, as you say, it's slightly different scales. But the running is actually going to cause this whole black tail to shift upwards or downwards. So this is something that we would then notice. So it's not going to produce an overall difference, an overall shift. It's just going to be this black tail is going to shift up or down depending on the running. And this is something that spectral distortions would be sensitive to.
And that is because the running affects the smaller, like, distant scales.
Exactly.
Yeah, which haven't been constrained by Planck and wouldn't be constrainable by S4.
Yeah, so Planck is of course limited by cosmic variance on one side and by the scales it can probe on the other side. Spectral distortions really extend this level arm. They give us new K values, several orders of magnitude more in K values that we can actually probe. And this is where the running becomes more noticeable. So then we can move on to what is basically my favorite plot from the paper. So now we look at the constraints on decaying dark matter. So we focus on the case of the fraction of dark matter that has decayed versus the lifetime of the dark matter. So now it's the opposite to before because the shaded region is now our excluded region. So the whole blue region is what is excluded with Planck and FIRAS. So this is our current constraints. Now the green region is what we could do with Planck plus Pixie. So this is just with Pixie. And if we look on the left for smaller lifetimes, we gain several orders of magnitude by going from the blue to the green. This is a whole new region of parameter space. And then if we look at the yellow orangey one, this is Lightbird plus CMBS4 plus Prism. We see that to the right of about 10 to the 12 in lifetime, we improve a bit, but not substantially. And to the left, we would improve on existing measurements from Planck by many orders of magnitude. This is the type of plot where we really see the synergy because CMB anisotropies are sensitive to lifetimes from 10 to the 14 upwards, essentially. And from 10 to the 14 downwards, spectral distortions are more sensitive. So basically you can cut this plot in half, kind of where the dip is. Everything to the right is already constrained by CMB anisotropies. Lightbird and CMBS4 will already give us very good constraints here. But everything to...
Sorry, go on. Sorry.
Everything to the left here is something that we need spectral distortions for. Without spectral distortions, we'd still be in the blue region.
Is there a good physics intuition for why it's the shorter lifetimes that would be more probable by spectral distortions?
Again, it's the scales at which they become dominant.
Okay.
So shorter lifetimes, they would inject energy into a way that wouldn't necessarily cause anisotropies, but it would definitely cause spectral distortions.
Okay. Okay. Okay.
So for comparison, we also show measurements like BBN, because BBN physics is also sensitive to dark matter decaying. This is in the red dotted line on the left-hand side, the red dashed line, sorry, and the black dashed line. And this is from two different papers, one from 2005, one from 2017, using different techniques to extract data from BBN. And again, it's better than CMB, but it is still behind spectral distortions. So I think this is really one of the plots that makes our point clearly, because we have disentangled regions of parameter space, one that can be constrained with anisotropies and the other with distortions. We get a very, very similar plot if we move to the case of primordial black hole evaporation. So this is the same cases as before. The blue one is what we have currently with Planck and FIRAS. There's also BBN shown for reference. And the green one is what we would get just with PIXI, which is already technology from 10 years ago. And the orange one is what we can hope to get with PRISM in the future. So a comment on this calculation. So a lot of people have, of course, studied primordial black hole evaporation. We actually found a new way of doing this where we take into account QCD confinement issues, which were not taken into account before. Okay. So we just want to I pointed out here because on the right-hand side, you can see that if we compare to previous studies, like what we call P19 or S18, we're almost one order of magnitude better already with Planck. And this comes from our improved treatment of the primordial black hole evaporation. Because obviously we'd hope that we would reproduce existing bounds, but here we have a reason why we're one order of magnitude better than previous bounds.
Is the location of this peak where it changes from anisotropies having strongest bounds to the spectral distortions having strongest bounds, is that kind of like the time at which stuff would be decaying at the same time as the CMB is forming?
Yes, yeah, so it really depends when this decay takes place.
Yeah, so to the right, the CMB's temperature spectrum can't be changed because it's already been made, but the kind of background expansion can be changed. Whereas to the left, you change the actual spectrum, but the background expansion isn't so important, or?
Yeah, so to the left is more early universe physics. This is why BBN is sensitive to the left of the plot as well. CMB is sensitive more to stuff that's happened slightly later on in the evolution. Okay. So this is actually the case of stuff that happened early on, so between BBN and CMB essentially. It has a bigger impact on spectral distortions than on anisotropies at this point. Cool. So this was the last figure I wanted to show here, and this is just another case where we show how much spectral distortions can contribute. So we're of course not saying that spectral distortion should be taken alone, but we really wanted to highlight that if you consider the CMB, temperature, polarization, lensing, you're still missing one piece of information, which are the spectral distortions. We hope to build this unified code that can do everything for you.
I mean, I guess the message is in your title that it's not the spectral distortions on its own, it's the synergy between them and the
Exactly, it's the combination of both that is really going to allow us to push all of our bounds to new orders of magnitude and to new regions of parameter space.
Thinking about, oh, sorry, go on.
I was going to say that we focused on some test cases here, but there's a lot of other models that we just mentioned and didn't focus on in this paper. For an example, dark matter interacting with baryons is going to heat the photon bath. Dark matter interacting with photons is going to heat the photon bath. These are models that we have the framework in place. It's just it's actually future project is to constrain these with spectral distortions as well.
Yeah, so this was actually sort of what I was about to ask a question about is suppose someone does work on one of these other types of physics, like is the class 3 or class 4? I forget which one you said.
Class
3. Like, do they have to modify the code in any way for their specific I mean, I guess it depends on what their specific physics is, but
yeah, it depends on the model you want to work on, but this is always the case with class. So class does not come with an infinite amount of models.
Right.
So we try to cover best cases here. So if you want to study primordial black hole evaporation, everything's in place. Okay. We currently have a version of the code, or there is a public version of class where dark matter baryon interactions are already implemented.
Mm-hmm.
Then you would just need to merge that code with our new one, implement one line of the heating function, and you're set to go.
Okay.
But if you have a new model that class has never heard of, you're going to need to implement it at every level in class. Okay. So it depends. For an example, models of inflation are already in class. So you can constrain a lot of different inflationary models with spectral distortions without needing to do many modifications.
Yeah. Because they'd affect in, the in running and things like that, and they're in it away.
Exactly.
So you started to get into this. So just complete those thoughts. Where to next? So
we actually have 2 papers already in the pipeline using this framework. So in this one, the first one was focused on the synergy. On the second paper, which is in collaboration with, I think, a Paris group, is actually focusing instead on at which sensitivity we would obtain this synergy. So this is really aimed at people designing the experiments to know which sensitivity threshold we need to actually reach this enhancement. So at which point do we start noticing the effects? And then there's another paper. So throughout our first paper, we completely ignored all foreground removal and all nuisance parameters. So all of the bounds I presented are slightly optimistic. But I mentioned before that several people have already wondered about at which point do we need to consider foregrounds, how do we need to consider them? So for another paper, we've completely implemented a foreground treatment. It's currently in the testing phase, and we're going to use inflationary models as an example case to test our foregrounds. But then we expect that once that is tested, then we will actually have a full treatment with foregrounds. So
this is something for which we do actually know the foregrounds already that we expect.
We can base ourselves partly on what was done for CMB anisotropies, because Planck obviously already had to do a lot of work in terms of foreground removal.
Yeah.
So we base ourselves on that. We know more or less what contributions we're going to have. We're going to have galactic center, we're going to have dust, we're going to have the cosmic infrared background. But then there's also some which are specific to spectral distortions. But again, this is something that has already been worked out. So you can already find this within the literature. We're now just unifying this within our code.
And is it partially also because a lot of the frequency dependence of stuff in the galaxy is sort of power law-y, so that it's easily removed? You don't have to. I'm way out of my my expertise here, but it looks like power laws, so it's more easily removed, because otherwise it could just be that it looks exactly like a spectral distortion and we're just stuck. But
yeah, this is the problem, that there are some of these foregrounds that can mimic the signals that we would expect. So the idea is trying to account for these. Like, we will always have this background level, which is going to be this foreground, and we quantify this with nuisance parameters. And then some of these are going to be entangled, so your dust across different angles is going to be entangled. So then you kind of put all of this together into a set of nuisance parameters, like what was done for Planck. And then you marginalize over all of this and then explore the cosmology.
Cool. So just before I ask you the final question, do you want to just repeat the 2 things that you wanted people to take out of this, so that now that they've listened to the talk?
So the first thing is really that spectral distortions are an untapped resource, because the theory is there and we're just missing an experiment to actually get the bounds. So it's really something that is waiting for us to exploit it.
And it's been waiting for 25 years.
Exactly. It's just there waiting for us. And the other message is that class 3 is going to be an amazing tool that's going to compute spectral distortions in parallel with anisotropies. And it's actually very timely, because class 3 should be released this month.
Okay, cool.
So within a month, you should have class 3, which comes with a whole new bunch of features, including spectral distortions.
Cool. And so then the last question that I've asked everyone so far is, like, outside of your own research, what's the most interesting thing in cosmology at the moment?
Yeah, I feel like I could kind of cheat here, because for me, the most interesting is the Hubble tension, but a lot of my other papers do focus on the Hubble tension.
Yeah, I mean, so far, 50% of the answers have been people talking about their own research, but yeah, so you can talk about the Hubble tension for a bit if you want.
So I think other people have already covered that on the talks here. So outside of the Hubble tension, something that I think is really, really fascinating is what we're going to be able to do with gravitational waves. So we're already it's a field that's very much in its infancy. We've had 8 or 9 confirmed signals from LIGO and Virgo. And I feel like this is just scratching the surface of the iceberg. We already know that the more data we get in terms of gravitational waves, the more we're going to be able to test. Even things like the Hubble tension, can be helped with gravitational waves, because we can use gravitational waves as standard sirens to get a measurement, an independent measurement of the Hubble constants. And I think this is something that if I wasn't in early universe physics, I would definitely be in gravitational wave astronomy, because it's a field that has so much potential and it's so interesting to watch it develop currently.
It's so new as well. I mean, new in a kind of observational sense, not I mean, yeah, people have been working on it for decades, but
but now we actually have the technology to measure it. It's still so amazing that we've been able to measure these gravitational waves.
Yeah, cool.
So that's completely away from my own research.
So thank you very much for taking the time to talk. And if anyone has any questions, they can ask them, and I'll pass them on. And
thanks for having me here.